Hi, everyone. Welcome to our Hangout with David Sliski from the Harvard-Smithsonian Center for Astrophysics. And myself, I'm Megan Ferreter. You hear from me all the time in emails from the Transcription Center, as well as hear from me on tweets and on Facebook and Tumblr as well. We have a lot of exciting things to talk about today in relation to these DASCH logbooks that you've been transcribing. I hope you're as excited as I am to hear about all of the things that you're doing and the discoveries that can be made through the data that you're transcribing.
Sorry, I'm on a Skype call.
We have completed 4 of the logbooks so far in under a month, which is pretty amazing progress. So we've done MF15, MF16, MF17, and MF18. And these are logbooks that were related to a specific telescope that was taking observations in down in South Africa. And then we also have numbers 19 and 20 in the Transcription Center. And David's going to tell us a lot more about these logbooks. We're at 79% on logbook number 19 and 45% on logbook 20. And then we have MC9 added in as well. So I'm going to introduce you now to David and let him have the floor here. But let me tell you a little bit about his interest in the different kinds of projects that you're working on. So he tells me that he's been interested in astronomy ever since his father took him to the Harvard Observatory when he was 10 years old. And he knew from the beginning there in his search for aliens, scanning the night sky, that he wanted to do this for a career. He's had a lot of really interesting roles so far. He graduated from UMass Amherst in 2010 with a degree in astronomy and physics. And he was accepted to an NSF-funded internship at the Maria Mitchell Observatory. He's also been to Australia and worked with the Australian National University on detecting gravitational waves, and he even flew a NASA ESA mission out of Tahiti to monitor ESA's largest spacecraft. If you have any questions about these things, I'm sure he'd be happy to answer that as well. And then in 2011, he came on board with DASCH to help assist with digitization, preservation, and figure out how to get these kinds of logbooks and other things streamlined into a really effective workflow, and then had the good sense to get in touch with us and help us bring these projects out to you volunteers so we can work together to make new discoveries using this data. So I'll turn the floor over to David here, and let me remind you while you are watching, if you have questions, you can tweet us at TranscribeSI or make a post onto the Google Plus page, and hopefully we can get those questions answered and follow up with you as well. All right, David, here we go.
Hi, everybody. Pretty excited to be here. I'm at the Harvard-Smithsonian Center for Astrophysics in Cambridge, Massachusetts. What you see behind me is one row of glass plates, each cabinet containing about 3,000 glass plates. We have something like 500,000 glass plates in our collection, which we're attempting to digitize. And the main reason we're part of the working with the volunteers is to transcribe the metadata associated with each plate. And when I say metadata, I mean the date and the time of the exposure and its location in the sky. And you can see behind me there's a picture here of what's the Magellanic Clouds, and that was taken in the southern hemisphere. And without the data of understanding when it was taken, the science that we can extract from them is useless. So without your help, none of the science that we're producing can be of any use. So I wanted to briefly share some pictures with you about some of these telescopes and some of the other things which we're seeing. So here, I think that will work. So one of the major telescopes that we'll be working with through the Transcription Center is this MC telescope, also the MF telescope, are kind of the 2 major ones we've talked about. And here you can see the major telescope in the middle around kind of what's called a fork mount. And what's in this shroud kind of in the back is where you would put the glass plate. Some of the things that were discovered on these various telescopes, the first kind of starting off in the parking lot here at the observatory in Cambridge in 1885. But in 1888, they discovered the Horsehead Nebula, and if you go onto our Twitter account, you'll see there was an article written about its discovery and why it was exciting. And you can kind of see here with my mouse, hopefully, the Horsehead Nebula kind of turned on its side underneath the bottom left star in the handle, or in the dip in the belt of Orion. And to the left, you'll see a composite image taken by Hubble with kind of very cool color. Another discovery in kind of in the middle here, you'll see something that looks like an O and a P and an arrow pointed to it. Inside of this circle is a moon. This is the moon Phoebe, and this was the first satellite of any planet that was discovered with a photographic telescope, not visually. You can see here's a picture of the moon in the bottom right-hand corner. This was discovered on the 24-inch Bruce telescope, something we may be working with a little bit later, and that was on these large format plates, which you can see kind of behind me. Another thing, while it wasn't discovered here, you can see Planet X. This is Pluto, which I'm hopeful many of you are familiar with. While it wasn't discovered here, the creator, the person who made the lenses for the MC and the MF telescope, was the same guy who made the optics for Clyde Tombaugh, who was the guy who was credited with the discovery of Pluto. So there's a lot of exciting, interesting historical ties with both the people that were involved and the instruments themselves. One of the last discoveries I wanted to mention was the discovery of Eros. This is what's called a near-Earth asteroid. It is one of the larger rocks in between Mars and Jupiter, and this is one of the things that kind of helped identify or reposition the astronomical unit. By looking at its position over time and measuring it, what's called its ephemeris, we were able to better define the distance, the average distance between the Earth and the Sun. Hopefully some of you guys are now familiar with seeing some of the logbooks. Here's just an example. You'll see at the top instrument, it says 16-inch Metcalf. This is the MC telescope. You'll see the date prominently displayed in the upper right-hand corner. And in the left, you'll see various plate numbers with the coordinates, the right ascension, the declination. We'll talk about what that is in a second. The start time of the exposure, what we're very excited to get from you guys, and the stop time over here, and some other comments. Megan asked me to show, how are we doing what we do? And so after we pull these plates, after you guys have typed the metadata or other people have previously, we pull them off the shelves and we photograph them at this table. There are two cameras, one that photographs the jacket, so any information that's on the outside of the jacket in the plate, and another that will photograph the plate itself and capture any of the annotations that were left on it. After it's been photographed, we have to clean all the markings away, and if you have questions, we can talk about that. But once it's clean and it's in a somewhat pristine condition, we digitize it, and so we in a second stage. And in this configuration, we have two 8x10 plates that are loaded in here with a telecentric lens and a camera up top. And what this allows us to do is that actually, instead of just taking one picture of the plate, we take 60 pictures of the plate and then stitch those 60 tiles together back to create one image. And that one image, when it's all the way what we call mosaicked back together, is roughly 1 gigabyte in data. So it's a pretty data-intensive project, and we expect more than a petabyte of data at the end of the day. And when we were first thinking about this project more than a decade ago, that was an unwieldy amount of data. Today, IBM and Microsoft and other people talk about a petabyte of data pretty easily. One might wonder why are we interested in this? What can we discover? What's the purpose of going back and analyzing these plates? And each plate has something like 30 to 50,000 stars on it, many of which have not been measured before. In fact, probably most of them haven't been. In this particular case, you'll see four slides from 4 different plates. In the upper left-hand corner, you'll see that there's basically no dots, kind of empty. In the second one, you'll see that there's kind of this white dot. In the third one, you'll see that there's a white dot, and in the bottom one, you'll see that there's kind of nothing. And what this is showing is that between June of 1945 and August of 1945, there was an outburst. Something very exciting happened. This thing which was invisible became visible. And then less than a month later, it disappeared again. And so you say, well, what is this? What is causing this dot to appear on the sky? Is it just some defect with the plate, or is it real science? And my boss, the principal investigator and a professor in the astronomy department here, Dr. Jonathan Grinley, evaluated this and understood it to not just be a defect or some random thing, but to actually be a black hole. And what I mean by that is that in this particular configuration, there is a black hole and there is a small star, and the black hole is like sucking parts of the matter off of the small star, and that kind of falls onto the black hole. And once out of for about a couple of weeks, every 50 years, some of this matter that's falling onto the black hole gets excited and gets shot out of it. It doesn't all kind of fall, like, if you're at your kitchen and you turn your sink on, not all the water goes directly down the drain. Some of it splashes to the sides. And so every 50 years, some of the extra matter that's kind of splashing to the sides gets very bright, and we can notice it. And so this is one of only 2 of these 25 that we've ever seen have kind of a second historical outburst. And so the very exciting thing is, for the first time, we'll be able to probe how often these things occur and how many of them there are, and how in the universe or in the galaxy we can figure out how to make these things. These are all questions that are currently unanswered by astrophysicists today. Well, looking at these pictures is nice. You might say, well, how do astronomers visualize them? And that's what this plot, this is called a time series. And so on the x-axis here, you can see the time. You can see 1900 on the left and 1975 kind of on the right. And on the left, you can see magnitude. This is effectively brightness. And so when we plot all of these points on this time series, we call this a light curve. And you can see over here in kind of 1901, here was another example of that kind of event where there's an outburst where it gets to be about 5 times brighter in a very short amount of time and comes back to kind of its similar stable mode. So while I mentioned earlier we've been doing this for about 10 years, some amount of the metadata had been transcribed previously, but we're looking to try to complete it. And we've been scanning some of these plates and trying to understand how to do this production. How do we scan them all? How do we extract all of the data? So to date, we've scanned about 80,000 of the 500,000 plates. And here's a map on the sky and what's called right ascension and declination. And when I'm saying those things, you can think of them exactly the same as longitude and latitude, except for they're on the sky. Latitude, as you know, plus 90 degrees is the North Pole, minus 90 degrees is the South Pole, and 0 is the equator. It's the same thing for declination. 90 degrees is the North Celestial Pole, where the North Star is. 0 is the celestial equator, and minus 90 is the South Celestial Pole. And then instead of having longitude as far as, you know, so many degrees east or west of the prime meridian, we use hours. And you can think of the reason we use hours instead is because it takes 24 hours for the Earth to rotate, and so it's a natural unit to pick. And so the hope is over the next 3 years we will be able to digitize the rest of the collection, but we'll only be able to do that if we have the metadata for the plates so that we can pull them off the shelves and then digitize them and make the science available. So I think that's just a little bit about the project. Any other? I think that maybe answers a bunch of questions about what we're doing. Does that make sense, Megan?
Yeah, that's great, David. It was really interesting to hear that what we're actually doing is a combination of citing or finding all this metadata, but also helping to confirm observations that have been already observed and expand that data as well. Thank you for sharing all of that information. I think we were also wondering a little bit about anything you can tell us a little bit more about the history behind the people and the technology that were making these, capturing these observations. I know some of these logbooks, and as our project summary describes, have talked about and have been covered in popular culture programming like Cosmos and things like that. Can you share a little bit more about that with us?
Certainly. So one of the two big moments in the history of astronomy happened inside of this collection. The first big one was in 1850. They took the first photographs of stars. These were not what you would normally think of today, but they're called daguerreotypes. And that was on what's called the 15-inch Great Refractor, which is about 200 feet from where I'm sitting. And the understanding of how photography could change astronomy, because things, as I showed you in the light curve, can take a very long time to change. So by being able to image the night sky, you can objectively measure it later on. And so with the invent of photography, and then here the invention of astrophotography, that allowed the fourth director of the observatory, Edward Pickering, to go on a quest to photograph both the northern and southern hemispheres. And so kind of beginning in 1885, he set out on this quest and started to take tens of thousands of photographs per year once he got ramped up with the correct telescopes. And by the early 1900s, 1909 into the 1915, a woman named Henrietta Leavitt noticed that some stars in the Small Magellanic Cloud and in the Large Magellanic Cloud varied, and they varied with a particular period. And she noticed that some of them that seemed slightly larger would get brighter over a longer period of time and then shrink back down, and then some of the ones that were smaller would have the same kind of period, but they wouldn't get as bright and their period would be shorter. So she came up with what's called the period luminosity relationship. And this was the relationship that Edwin Hubble uses when he finds these same Cepheid variables in the what was called the Andromeda Nebula. Because at that time in 1921 there was a famous debate between Harlow Shapley and this other guy Curtis about how large the universe was. At that point we understood that the Sun was the center of the universe and the Earth went around the Sun, but we weren't quite sure where our place in the universe was. And so one argued that these fuzzy blobs like this were external and were not part of the Milky Way. One of them argued that they were part, but they both kind of agreed that the size of the universe was 25 to 50,000 light years. And these were, one guy said 25, one guy said 50, but that was as big as they could imagine. 3 years later, Hubble uses that discovery of these Cepheid variables and finds that the distance to the Andromeda Nebula was 1 million light years away. Completely, outside the ballpark, any type of error measurements that the other guys could have predicted. And this opened what I would call the second era, or the second phase of the Copernican revolution. And that our understanding of the cosmos goes from we are part of millions of stars inside of the Milky Way universe to hundreds of millions of stars as part of hundreds of millions of galaxies, and now we understand hundreds of billions of stars and part of hundreds of billions of galaxies. And our uniqueness shrank in order of magnitude in that case. But without Henrietta Leavitt, without these glass plates, that discovery wouldn't be possible. The other thing which was highlighted on Cosmos was there was a woman named Annie Cannon, and she looked at what are called spectra plates, and as if you take a prism and you put it in front of the light from the sun, it spreads apart into the rainbow. If you do the same thing with the stars, you get different rainbows for different types of stars because they're different types of colors. And she effectively cataloged something like 500,000 of these, and this is what creates the modern catalog today of O, B, A, F, G, K, M. These are the different types of stars that are brighter. The O types are the biggest and the brightest, and the M's are the smallest and the least luminous. And so some of the most fundamental things in our field, some of the most fundamental discoveries of the early parts of the 19th century come from the women and the men who were working here and from these glass plates.
That's fantastic. Thanks so much for sharing that, David. So we thought, volunteers, that we would take the opportunity that we have David here to talk with us about some of the kind of consistent issues or questions that we have with transcribing the logbooks. We get a lot of questions from you all about how to format certain things, sometimes to do with, for example, start and stop times within the logbooks, and other questions about making sure that we're providing consistent metadata. So I'm going to return the camera back to David and let him explain and give a little bit of guidance on anything that he's observed as he's been going through the transcriptions that you've been making.
Cool. So thanks. I think overall one of the things I want to share with the volunteers is the effort between the transcription and the reviewing has been phenomenal. It's been way above anything we would have expected, and given a lot of the transcription work we've done in the past, we've seen 10 to 20% error rates in some part of the line for the plate. In here we're seeing 1 error per page or something like that. Completely much smaller, which means the staff time to fix these things, get them into our database, and get them scanned is much faster. So that's a huge help. So before anything else, that's a huge thank you to that. I did want to review a couple of things, though, as far as formatting was concerned with you guys. Maybe less about the specific errors, but more about just kind of understanding what you're typing. Because I think maybe different than a lot of the other transcription projects where you're really trying to capture exactly what you see, here we're trying to extract the interesting science, not necessarily the interesting cultural histories with some of the ways they annotated that. And let me give you an example. Let me screen share. Okay, so on this plate, this is from the MF logbook, page 42, and you'll see in the number column you will see a check mark and a dot in front of 18838, and then later down here you'll see a check mark and a colon and 18843. The check mark and the colon and the check mark and the dot were added after the fact, and are fairly irrelevant from a science point of view. While they're interesting maybe historically, so for instance 18838 would have been written at the site when they recorded that plate, and maybe when the logbook and the plates came back to the observatory, somebody said, yes, I got this plate, and yes, I checked this plate, and they're in existence. but knowing that for our purposes is less exciting. So for this field, I would, if I was to transcribe it, I would ignore the check mark and the dot and just type in 18838. And this you can see in the transcription instructions that we just want you to type this number. It should be a 5-digit number. Next, you'll see something called the class column, and then you'll see a bunch of ditto marks underneath it. The class L here designates that it is a blue sensitive emulsion. And so what that means is that you can take, astronomers always take black and white images. So all the images that you've ever seen from Hubble were originally black and white images. But we put a filter in front of them to select only the blue portion of the wavelength or the red portion of the wavelength. And because we know how we've designed these filters, we can then recombine everything after the fact and create an accurate color representation of that object. And this allows us to pick out different wavelengths of light which are specific to some type of transition or some type of event that's happening. So we can really delve into both the science and the beauty artistic things by having these filters. So, and back in the olden days, they actually didn't have that choice. The emulsion that they were dealing with was only blue sensitive. And so here you have a class L, and an M down here later signifies that it's a multiple exposure. There are multiple exposures on that given plate. The other, I think we've talked a little bit with some of you that the ditto marks, we would ask you just to copy what's above it. Some of you just try to transcribe exactly what you see. But in this case, we know that it's L all the way through. We know that that makes sense, that they would have been taking a lot of blue plates. So we would just ask you to use the word L here. Object, this for me is one of maybe the more exciting and the more challenging things to figure out. So for instance, for 18842, kind of in the middle of the page, kind of looks like a bunch of weird, but this says focus. A little bit below it says MWF216, and then a little ditto mark for 217 and 218. These are objects inside of the MWF catalog, and to be honest, I don't actually know what the MWF catalog is. And there's a lot of catalogs which are since extinct, or people don't refer to them anymore. And so it's sometimes interesting and potentially useful to know that they were trying to image an object in that catalog, and they may have misclassified it when we have our new catalogs today. So from a scientific standpoint, it might be interesting to compare what they thought they were imaging back then to what we know that they're imaging today, and have that kind of compare and contrast. We talked a little bit earlier about what right ascension and declination are. These are the same things as longitude and latitude on the sky. But maybe more interestingly, I want to explain a relationship between the right ascension, the start time, and the observed hour angle. So the start time is, when you are sitting at the telescope and you open the shutter, the beginning of the exposure happens at what time, and that's a pretty easy thing to understand. The right ascension also, the star has some coordinate, just like on Earth I have a latitude of 42 degrees and a longitude of, I think, 72 degrees west or something in that approximate. Just like any star in the sky would have a declination. In this case, the first one has a declination of -82 degrees and a right ascension of 5 hours and 30 minutes. The trick here is at that location where they were imaging that star, where is it relative to you in the sky? And that's how we figure out what the observed hour angle is. So the observed hour angle is the difference between the meridian and its location. And the meridian is the line in the sky which separates the eastern part of the sky and the western part of the sky. And what I mean by that is that anything on the eastern side of the sky is always rising, and anything on the western side of the sky is always setting. So in this case, we are 1 hour and 28 minutes east of the meridian, and so if we want to know where the position of the star is, we would add 1 hour and 28 minutes to the start time of 4 hours and 2 minutes, and that's 5 hours and 30 minutes, and that's exactly what the right ascension is. And for those of you who are interested, this is exactly how we told time, or how we calibrated our clocks 100 years ago. One of the major functions of the Harvard Observatory in the late 1800s was to do this measurement. They would know what the positions of the stars were very accurately. They would know what our longitude and latitude was very accurately, and so they would be able to say and calculate their local time, and they would sell this as a service for the same way that you would buy your cell phone service or something like that. So if it's east of the meridian, we add it to the start time. If it's west of the meridian, we subtract it from the start time. And you'll be able to go through and as a quick check, if you ever want to check that, that's if you're unsure about something, that's how I always check to see if I'm transcribing correctly. Now, don't be too afraid if you're unsure. Don't spend too much time on it. It's not we don't ask you guys to be 100% accurate, and in fact, if it takes you twice as long to be 100% accurate versus 98% accurate, I would say just be 98% accurate, because we have software at the DASCH team that we will run over these and do a bunch of these calculations and compare them, and if we see an error, one of the staff members here will go back and correct them. And those are a couple of those errors that we see. Now, occasionally, those are actual errors in the logbook, and somebody messed up. They were out in the middle of the field in 1933, and it was 2 o'clock in the morning, and they wrote a 2 instead of a 1. And so it's our job to interpret that and tell the scientists who are going to use the data what they actually meant. But you as transcribers should never have to worry about that. Other things which you can see is that there's one of the last columns to the right of the stop time is the exposure time. Again, a simple check should be if you subtract the stop time from the start time, you should equal the exposure length. One mistake that I know was definitely pointed out is that people used to transcribe the Fri-sat. That's irrelevant from our point of view. While I know it may be historic, we can always go look that stuff back up. If we know the day, we can always go back and look that up. But for our purpose of trying to get the data as fast into the logbook and eliminate as much transcription for you guys as possible, we've decided that that's not quite useful. So if you just type the first 3 letters of the month, and in this case 20-21, and then the year, that's fantastic. And I think the last thing, in this remarks column, which I think may be most relevant for you guys, and I know came up in a question that I'll get to in a minute, this is really kind of where I think this transcription can be exciting. And I mentioned earlier there was the discovery of Phoebe, there was the discovery of the Horsehead Nebula, and this is where, if the director's like, hey, there's a supernova that's going off, or hey, I think there's maybe an interesting object over here, you can read through these comments, and maybe the person who's doing the observations will tell you, say, hey, from Edward Pickering, I was told that there may be something interesting here, I'm going to go image it. And so really you're rediscovering the initial discoveries that may have played an important role in understanding how astronomy evolved in the early parts of the 20th century. Hopefully, I think that. And I think one thing to talk about is we have a new type of log. This is from the MF telescope, which is a single telescope. We have a new series of logbooks which are coming online called the MC telescope. Let me go back to the beginning, if I can, and show you a picture of it. And this is important because the MF telescope, which is one telescope. But here you can see that there actually looks to be 3 telescopes on this mount. You can see one's kind of in the middle, one's on the top, and one's on the bottom. And they actually, in some cases, photographed with all 3 at the same time. And so that makes the transcription a little bit tricky. So I wanted to go over that very briefly with you guys as we just hosted the first logbook last week, and I wanted to show you how we might transcribe that. So here's an example out of the MC9 or the MC4 logbook, which we haven't posted quite yet. But in the left-hand column, you'll see MC, MD, ME, all with this 1014, 1014, and 1014. So I think the way that we would just transcribe this is you could leave the MC, in the number column, you would say MC space, MD space, ME space, 1014. And then that just shows that that's all of these telescopes are going to take this exposure. Now to the right, there are 5 exposures, and they have right ascension 9 hours and 15 minutes, but you can see they have 5 different start times and 5 different stop times. So this would be 5 lines of transcription in the Transcription Center, with the plate numbering system being slightly different, where we would indicate these 3 telescopes. And the MC is one type of telescope, the MD is another type of telescope, and the ME is another type of telescope. So anytime we're talking about 2 letters in front of a number over here on this side, that's usually referring to different telescopes. Lastly, and I've talked to Megan a little bit about this, but one of the more challenging things to extract from this is in the remarks column. And you will see there's a series of 5 dots. And you'll see that there's, on the left side, there's a little bit, a medium-sized dot, and then there are 3 small dots, and then 1 big dot. And underneath it, you'll see that there's an 8 with a little squiggly M, 1 with a little squiggly M, 1 with a squiggly M, 1 with a squiggly M, and 64 with a squiggly M. And above it, you'll see a 2, 1, 3, 5, 4. And so what this means is on this plate, they didn't take them in order 1, 2, 3, 4, 5. They actually changed the order. And for us to extract the science, it's important to try to understand the order of the exposures. So we might tell you, say, in brackets, say the order of exposures equals 2, 1, 3, 5, 4, and then space the 8 minutes, 1 minute, 1 minute, 1 minute, 64 minutes, and to help us try to identify that. And so this is a challenge, though, and maybe as these problems come up, we can discuss them more. But I think that's how I would approach it right now. Megan, do you have any other questions, or does that maybe cover some of the transcription problems that we've seen come up with different things?
All right, great. Hopefully we still have broadcast. I dropped Wi-Fi there for a minute, but thank you for explaining all of those details, David. I have a question that's related to how-to in from Twitter, which is from Michelle asking, do you want the data entries changed if the comment section says, for example, that the RA should be different?
So I think my answer to that would be probably not by the transcribers. I think that that's a great thing to leave in the comments area, and I think that it's a great thing if you guys leave it in the box down below. And that's something that we will review, because sometimes the reason why that would come up is that, for instance, they would take the plate and maybe they knock the telescope to the left or a little bit, but they didn't know this. And then it gets shipped back to Harvard, and somebody evaluates and says, oh, it's supposed to be 16 hours and 15 degrees in declination. And they're like, no, actually, it's 14 hours and 15 degrees. I think that can be a tricky thing to interpret sometimes, because you don't know who's making the correction. It could be a high-level staff member from 50 years ago. It could be somebody who misidentified it. And so I think it's fantastic if you guys just leave that kind of comment there, and we as staff will look for that.
Okay, that's a great answer. I'm just tweeting that back so we can have that on record there. So we have come to the point now where we'd like to invite more questions from the volunteers. We got a few questions ahead of time, so let me just take a look at those real quick. David, one question that we've talked a little bit about the two different kinds of logbooks that have been brought into the Transcription Center so far, the MF logbooks and now these MC logbooks. But one of the questions that we have is there a particular reason that you brought in, for example, the MF logbooks first? Is there a reason they were prioritized, or is there any decision-making strategy on which kinds of logbooks are brought in? I'm sure there's a wide variety of things that could be transcribed or metadata that could be useful.
Yeah, so I think the easiest way to understand that is I've made a big spreadsheet. We have something like 25 different plate series here, and some of them are more valuable from a scientific standpoint. Some of them are slightly less value, how do I define value? Define value by saying how many stars are there on a plate. And so certain telescopes have very large apertures and have very deep fields, but their field of view can be very, very small. Other telescopes can have an extremely wide field of view, so think of like a fisheye where you can see almost like 80% of the sky. From a DASCH perspective, from a community perspective, both of those are not very exciting. So I picked the middle ground, and I said, well, which telescopes do we have that are pretty big, but and give us a good piece of the sky, but aren't so big that they don't show enough depth? And so the MF and the MC and maybe the B telescope is what you'll see the MC is 16 inches in diameter, the MF is 10 inches in diameter, the B is 8 inches in diameter, and they have somewhere between 10 degrees or 15 degrees square on the sky, roughly. So those are from a science perspective, those are the most exciting things to have digitized, and those are our highest priority. And so inside of those, why do we start with the MFs versus the MCs? I thought the MCs were a little bit more complicated. I think those are, out of anything that we're going to transcribe through the transcriptions, that are maybe the most exciting, as is the least complete set that we have. But with these multiple telescopes, I wanted to start us with something a little bit easier, and we were already halfway through the MFs with our summer students, and so I kind of wanted to finish that up with you guys, and we're really excited on logbook 20 now, and I think we've got another couple maybe that got swept behind when we were doing our digitization of the logbooks. But so we definitely we try to think to ourselves what's most exciting from a science perspective, and then from there, how do we get things to you? What's the easiest thing to get to you as our volunteers, and just kind of work with you guys that way. Great.
I think it was really wonderful that you explained, or just maybe briefly mentioned there, that there are other people who have been transcribing some of these logbooks, to think about the fact that the volunteer efforts actually match up with in-person volunteer efforts as well, and that students are working on these, and that it's a really active and dynamic process of scientific discovery and creating this metadata that can be used. And we had another question that relates to the ways in which this set of data can maybe be integrated with other scientific research efforts. So Siobhan asked us whether or not you might be planning to share other portions of data that are coming out, for example, weather observations that are in the logbooks, with other scientific organizations who may be doing similar kinds of research or may be able to benefit from that data. Have you had any conversations with any other organizations that might value that information?
At least right now, as far as the weather is concerned, we certainly haven't. That's been an afterthought, I think, for us. When we were transcribing 2 years ago, we really transcribed significantly less data than what you guys are transcribing. We were pretty much doing plate number, start time, stop time, date, and a right ascension and declination. We were pretty minimal with what we were transcribing, and that was, as paid staff time, what's the best and fastest way we can get the data into the pipeline and allow that to happen. So, but once we have a number of these records transcribed, I think it would be very exciting to go to different groups and study weather. Something else that's been proposed, I know, by Elizabeth Griffin, who works at the Dominion Astronomical Observatory in Vancouver, British Columbia, is that she wanted to look at, I mentioned earlier, these spectra plates, where you put a prism in front of the telescope and you get the kind of the spectrum out. She wanted to look at high-resolution spectrum of a star from, say, like 1900, compare it with one today, and understanding maybe the weather conditions that are going on then and now, but maybe try to track climate change and pollution control, because naturally the things that you're looking at with these spectra are the chemical signatures of the planet and of the atmosphere. And so if you know that the star should be the same, sorry, the star, not the planet, the star should be the same, that the thing that may be changing is our atmosphere. So it's one way to kind of look back and check these different things. So there's certainly a variety of possibilities that extend way beyond just these time series and light curves that I mentioned to you earlier, of possibilities with this collection.
Yeah, that's really fascinating. We have a question from Laura being shared with us on our Google Hangout page. Is there any issue with transcribing the 24-hour time format the way it is written in the logbook versus the actual defined format of 0000? For example, if the logger writes the hour as 4 rather than 04, does it matter if the transcription is one or the other?
Okay, so that's a great question, and that's something that we've definitely struggled with a little bit at time. And so I'll give you two pieces. So for the hour, if it's 4 versus 04, that doesn't matter. And so our software, how we interpret that, and the hour is fine. However, if they write 4 and there's a space and 2, and you just write 4 and space and just put a space mark in 2, that becomes a problem, because we don't, you don't know if it's 2 minutes or if it's 20 minutes or what happened. So for the minutes column, it's important to have those 2 digits, but for the hours, it's not. And sometimes you'll even see, in some cases, they list the seconds. Sometimes they do hours, minutes, and seconds. So the leading 0 at the hour is not important, but a leading 0 for the minute or a leading 0 for the second can be important for formatting and stuff like that. That's a great question.
Yeah, thank you so much for via tweet as well recently, and kind of gave the same advice that it needs to make some specification for the minutes and the seconds as well. Also, when we were talking earlier about, you were explaining, that this data is helping us to identify things like outbursts, which indicate black holes. One of the questions is, I think the question was meant in a more serious way about what is the best case scenario, what is the thing that you're hoping to find. But I'd like to know, just on your end, David, what it is that you would really hope to find by using this metadata. What would be the best possible discovery, the almost unimaginable, as you gave the example of, Hubble using research and discovering that the universe was so much, or we had not just millions of galaxies, but billions of galaxies out around us.
So I think, my field of expertise, what I've been working on from a research perspective, is exoplanets. So I think I'm more qualified to give you a response from them, and I can talk maybe a little bit more vaguely about some other things. But one of the most exciting things that appears in the news pretty frequently, I think there was one yesterday, the day before, are the discoveries of planets around other stars. I think the one that happened 2 days ago was there was a binary star system, so there's two stars going around each other, and each star had a Jupiter going around it, so it was this kind of like weird four-paired thing in this very interesting dynamic state. We're probably not expecting life to be there, but one of the most exciting questions that we've been able to ask since the Kepler Space Telescope has been launched are, how many planets are there? Where could there be life? Is there life elsewhere? And I think one of the first thing that you say is, all right, so there's so many planets. We've decided, the astronomy community's found so many, and we say the calculation rates, the occurrence rate should be that for roughly every star, there should be a planet. So for 100 billion stars, there should be 100 billion planets, although that number is still in question and it's going up and down. But the question is really, how many of those planets are in the habitable zone of their respective stars? And so what I would say to you is not only what stars in the habitable zone, but one graph I didn't show you is some stars can vary their brightness over a 100-year time period. And we found some new stars which had never been found before that had a 1 magnitude or 1.5 magnitude variation over a 50-year period. And that's like a factor of 3 or factor of 4 in brightness. So you can imagine, if your parents were outside and we were going around that star that was varying like that, that 50 years ago they would be that the surface of the planet might be 3 times brighter, or 50 years from now it could be 50 or 3 times cooler. So you go through all of these weird climate changes on a very fast time period, which would make it impossible to have life like us on there. So there's a very exciting possibility of probing the stability of stars, the possibilities for life, which are otherwise impossible with any other collection on the planet, because the only way to understand long-term trends is to evaluate long-term data, and this is the only collection on the planet that has 100-year coverage of both the northern and the southern hemispheres. So I think for me that's one of the more exciting things. But going back to Dr. Grinley's motivation, we don't understand how these black hole dwarf star companions form. We don't know how many there are. We don't know what fraction of the mass of the galaxy. People talk about dark matter and dark energy. Could that be black holes are obviously black. We don't see them. But if we haven't accounted for 99% of them, maybe that makes up some fraction of the mass in our. I don't know. I actually don't. So there's a lot of exciting questions that a data set like this gives you. And I think historically, the other thing is, well, we talk about Henrietta Leavitt and we talk about Annie Cannon and we talk about some of these famous women computers who worked here. We don't have specific pages. We don't have on this, look here in this notebook, or here, or look here, here's the story of them making that discovery. So I think for the first time we're making available this data to the public to uncover the story behind their discoveries. And I think I'm allowed to say this, but there's a prominent author who's writing a book on this, and it should be out, I think, by next fall, or I think that's about that, Davis Sobel, who wrote Longitude. And so there's definitely going to be a lot of exciting coverage coming up about these women and these stories and unearthing them. And many of these logbooks haven't been looked at by people in ever, or 30, 50, 100 years. So you get really exciting, really intimate experiences with very exciting data, and potentially for the first time, or being one of very few people to see that. So for me personally, that's one of the things that motivates me and makes me get up in the morning and gets me excited. So.
Yeah, that's great to hear, because that's what motivates me as well. And coming in is this opportunity to make all of our various transcription projects available in new ways, and in the same way that you're saying, ask new research questions, as well as better understand what we already know about these people and the research that they were doing. And as our volunteers consistently discover the relationships between the people who were doing research. And I just think it's really interesting that in the same time period, the start of this image collection was really in the same time period that much of the exploration that set the groundwork for the Smithsonian was also happening. It was a time of exploring our world and also exploring the worlds around us as well, which is fascinating. So I think we'll go ahead and wrap up now, but I want to ask one more question, which is if you could make some recommendations for our volunteers of places that they could find more information if they wanted to, let's say this is their first exposure to astronomy, if there are organizations or resources that they could access, or any sorts of connections that you'd like to give them for exploring other things and learning more about all kinds of research in this field.
So, I mean, I think I have 100 things come to my mind, and none, depending on which way we want to go. And so if you guys have any specific questions, feel free to tweet at me or send me an email. I think that I'm happy to respond to any of you guys. Have been so thankful for all of your hard work. A couple of things which come to my mind right away. If you want to go outside in the backyard and you want to see what's up, there's a wonderful program called Stellarium. It's free to download, really easy to use, lets you see what's up there. For context about the DASCH project, you can always go to the DASCH website. If you go on Google and you type in DASCH and then Harvard, it's the first link, or sometimes if you just type in DASCH, it's usually towards the top. You go to the project page.
Also find that page, the link to that, in the project description, so the extended description on the project pages, and also in the email that you will have received today about this Google Hangout.
And inside of that, there towards the bottom, there's something called DASCH in the News. And there are some really cool articles. George Johnson wrote an article in the New York Times in 2007 about us. It was great. We were most recently, I think we were in Popular Science and Scientific American. So there's some cool other, and we were in the Harvard, local newspapers and stuff like that. So if you want to get some backstory and see some different pictures of the collection, it's a great place to go and kind of get some understanding. Other things, there's something called, if you're looking to get more excited into astronomy, do more of this, there's something called the Astronomical League, and there are usually an amateur astronomy group somewhere within 20 to 50 miles of you, if not closer. I know that the Amateur Telescope Makers of Boston meet across the hall, and I know that some of them have been helping out with our project. We put an announcement out a year ago through the Astronomical League to call for volunteers, and before we launched with Smithsonian, we had a small group of beta testers to try to understand how we were doing this, and they were truly wonderful working with us, and that kind of helped set up the foundation of how we got this going. So there's all sorts of resources all over the place. A fun book to read if you want to go read more about this kind of stuff is George Johnson, as I mentioned, wrote a book called Miss Leavitt's Stars, and so that's kind of a fun way to kind of look through and detail some of that. Alan Hirschfeld just wrote a book, and I'm blanking on the, I think it's like Discoveries of the Cosmos or something, but I can put a tweet out about that, or we'll send a follow-up email. There's a lot of good books. I mean, I would also point you to Cosmos, with Neil Tyson, episode 8, Sisters of the Sun, that talks all about us. You'll actually see one of the logbooks, and I was really excited to see they actually got the accuracy pretty spot on, the colors, the margin notes, the lines in there. It was really well done. I was really excited. I mean, I caught a couple of little minor flaws, but I'm probably one of 2 people on the planet that actually knew enough to be able to, see one side versus the other. But it was really, really good. I was really impressed with the detail that team put together. So that's just, another fun way to kind of see how this meshes with popular culture.
Wonderful. Well, thank you so much, David, for being with us today and explaining, answering all the questions that our volunteers have. Remember, volunteers, if you have questions about these projects, you can either tweet us or tweet David or the DASCHdesk, which is a newly established social media resource on Twitter to help answer your questions about these projects. And remember that all the questions that you ask help us make better instructions for volunteers and improve the process of transcription to create more accurate metadata, which allows us to do more accurate research and make more discoveries. So thank you so much for being with us today, and hopefully if this has sparked some more questions or more interest, you can use some of these resources that David has provided for you, and we will catch you again soon. Thank you so much for all of your time that you spend with us, and we'll talk to you again soon. David, I'll let you do the last sign-off.
Thanks so much for all your help. We look forward to working with you guys in the future, and on to finishing logbook number 19.
All right, bye, volunteers. Thanks so much.
Bye.